Alright, I wanted to record one more video to make sure we have enough of information to go through some practice questions tomorrow or today. It's like 2 a.m. right now. It should be a short one. We'll go over breathing mechanics, surfactants, compliance, and elastance. Okay, does everyone remember Boyle's law from chemistry back in the day? Boyle's law basically states that for a gas, and remember inhaled air is a gas, the volume of the gas is like inversely proportional to the pressure. So that's stated here in red. So this is really good to keep in mind when thinking about breathing mechanics. This is cut off here, but if you compress a gas, right, in this case, if you compress it, you make the volume smaller, then that will increase the pressure. Okay, this slide is very important. Okay, so over here on the left we have a diagram of what's going on. This is the volume of the breath. This is the intrapleural pressure, and that is the pressure in the thoracic cavity, in a sense. You may also see transmural pressure. Maybe not. Scratch that. Intrapleural pressure, IPP. Okay, and down the bottom is alveolar pressure. So the pressure of that inside the actual alveoli, and everything. This is important. Is expressed relative to atmospheric pressure. Okay, so at rest, this is kind of a high yield point. At rest, the lung volume is equal to the functional residual capacity, and remember that is here. So that makes sense, right? At rest, remember tidal volume is just normal breaths in and out. You're not exerting yourself. So at rest, you'd be like right here. So the volume in the lungs would be equal to the FRC. Now, what happens when you take a breath in? The diaphragm and the external intercostal muscles contract. And what happens when the diaphragm contracts, this is important to remember, it goes down. So the thoracic space increases, right? That makes sense. And remember Boyle's law, we're increasing the volume of the thoracic space, so the pressure will go down, right? The inverse relationship. And we see this here, we're increasing the volume in the lungs, right? We're also increasing the space in the thoracic cavity, so the intrapleural pressure becomes more negative. Okay, that's very important. At the same time, the pressure in the alveoli is decreasing relative to atmospheric pressure. And we see this here. Okay, 0 would be when the alveolar pressure is equal to atmospheric pressure. So during inspiration, the alveolar pressure drops relative to atmospheric pressure. Now that creates a pressure gradient. Air wants to flow into the lungs because there is a favorable pressure gradient for it to do so. Remember, like a high to low, and so it's all relative in this case. So air wants to flow from high to low until it gets back toward atmospheric pressure, right? Then the alveoli. So at this point, the lung volume would be the FRC plus 1 tidal volume. Okay, that makes sense. Remember, this is inspiration going up. Plus 1 tidal volume. So, what happens during expiration? Basically everything's going to be the opposite. You have a relaxation of those respiratory muscles. The thoracic space decreases because as the diaphragm relaxes, it's going back up. So that's decreasing the space in the thoracic volume. And because of that inverse relationship, the IPP returned to its resting value, which you see here. Okay, and remember, at rest, it's still a negative pressure, but when you inhale, that pressure becomes more negative, and then when you exhale, it returns to that resting pressure. In the alveoli, what's going on in the alveoli is it increases relative to atmospheric pressure, so that this pressure gradient is reversed. Everything's the opposite, so air wants to flow out. You want to exhale. And the lung volume, as you can imagine, returns to the FRC. Okay, so, I wanted to touch on the mechanism of surfactant. Do you remember what produces surfactant? As a little review question. Type 2 pneumocytes, or type 2 alveolar cells. What does surfactant do? Decreases the surface tension. This equation here you'll also see called Laplace, I think the law of Laplace. Pressure equals 2T over R. T in this case is the surface tension and R is the radius. And this is a really important concept, how to think of the pressure, the P. So this is a collapsing pressure. So think of it as a pressure that wants to make the alveoli collapse, or the pressure required to keep the alveolus open. So as you can imagine, with a large alveoli, we have a large radius, which means there is less collapsing pressure. So even without surfactant, a large alveolus might be okay in the sense that it is less likely to collapse. But if you have a small alveolus, it has a smaller radius, which means that it's more likely to collapse, and that's where surfactant is really, really important in these, especially in the small alveolus. It does help the large ones, obviously, too, but the small alveoli is really important here. And that's because, remember, P equals 2T over R. Now what we're doing is we're decreasing the numerator, and it's 2T, so it has a greater effect on the pressure. So we're decreasing the pressure, and that means decreased tendency to collapse. So this is how surfactant helps keep the alveoli open. Another way to put it is surfactant decreases the pressure required to keep the alveolus open. Makes it less likely to collapse. Okay, let's talk a little bit about compliance. Okay, this is just a good thing to keep in mind. There are these forces. There's these lung forces and these chest wall forces. And just as a general rule, the lungs want to collapse by its inherent nature, and the chest wall wants to expand. Okay, and technically there's a compliance of the lungs, and then there's a compliance of the chest wall, and then there's a compliance of the lung chest wall system. But okay, so this first little bullet here would be describing inspiration. When the pressure outside the lungs is negative, the lungs expand and the lung volume increases. This would be describing expiration. When the pressure outside the lungs is positive, relatively, the lungs collapse and the lung volume decreases. Yeah, I think that's right. Anyway, compliance. So compliance equals volume over pressure. And this is illustrated here in the case of like a smaller alveolus with air entering versus a bigger one with air entering. So C equals V over P. So in the case of this small alveolus, the volume's smaller, so it's directly correlated to compliance. So it's going to have less compliance. In the case of B here, the volume is bigger, so equals V over P. So it's going to be more compliant. So what that means is, if you remember that picture in the previous slide talking about surfactant, is the larger alveoli are going to be more compliant. Okay, and the way I like to think of compliance is, and you'll see this term with veins, it's called venous compliance, is how good is it at handling the air that's coming in, right? Or how much can it expand when the air enters. Hopefully I explained that right. So how compliant is it? It's kind of an intuitive word, like how compliant is it? Now, where a lot of students get mixed up, myself included, is comparing compliance to elastance. When you hear compliance, think inspiration. Okay, this will help. And when you hear elastance, oh, it has an E and didn't even realize that. Think expiration. So compliance is a measure of distendability, like I said in the previous slide. How much can the alveoli distend, or how much can the lungs distend when you're inhaling air? Elastance, like a rubber band, is a measure of elastic recoil, or how good are the alveoli at snapping back down to their original size when they exhale air. This is really important. And these concepts are really high yield. Okay. So they're kind of opposites of each other. They're inversely proportional. And I probably will ask some sort of test question on the effects of either obstructive or restrictive lung disease on compliance or elastance, because you'll see those types of questions again. So in the case of a fibrosis, like a restrictive lung disease, that is a problem of, so remember, restrictive lung disease, you have trouble getting air in. And remember, compliance, think of it related to inspiration. So you're going to have decreased compliance in restrictive lung disease. Anytime where you have decreased surfactant, like respiratory distress syndrome, like of a newborn that's premature, this will be the case also. Let's see, pulmonary hypertension, congestion. So this could be a case of like heart failure. Right? Now, in the case of obstructive, like emphysema basically happens because surrounding these alveoli, you have this elastic tissue support, and Smoke is a very intense chemoattractant for neutrophils, and what happens is these neutrophils have proteases, and proteases break down proteases and elastases, and what they do is they destroy this elastic tissue support surrounding the alveoli. So as you can imagine, elastance decreases, the elastic recoil decreases, and that's why these patients have trouble getting air out because their elastic recoil is affected. You know, you can imagine if this elastic tissue support is destroyed, you know, air can enter fine, right? That'll cause this to get bigger because the compliance is increasing. Remember, they oppose each other. Really important. But like a old rubber band, that elastic tissue support is destroyed. So when the air tries to go out, it's going to be very inefficient. Okay, and that's why, if I can take it back to the forced expiratory volume 1 second over FVC, that is why you have a large decrease in the FEV 1 second. And so as a reminder, like something, an obstructive pattern would have something like 2/4 for this ratio, or 0.5, or like 50%. So it does decrease both, but this is the hallmark of the obstructive disease. Remember, asthma is also an obstructive disease. And normal aging, this makes sense. You lose some elastance as you get older. All right, how does surfactant alter pulmonary compliance? I'm going to go bring these up to explain it first, and then I'll answer it. So remember Laplace's law. Let's take it one step at a time. Surfactant decreases the surface tension, which decreases the collapsing pressure on the alveoli. Another way to put it, remember, it makes it so that less pressure is necessary to keep the alveoli open. So that means the alveoli can be more distendable upon inhalation of air. Another way of saying that is they have increased compliance. And if you want to see this in formula form, you know, when you decrease the denominator, you're going to increase the compliance. So increase. Okay. Oh, I just talked about this. So emphysema, you can read this. The elastic tissue support is destroyed. Therefore, these patients can breathe in somewhat normally. So they can breathe in okay. And actually, they have increased compliance. But they have decreased elastance, which the following effects does emphysema have on compliance? So I kind of just gave you the answer. Remember that compliance is opposite of elastance. So decrease elastic recoil means increased compliance. And this is the reason that you will hear the term air trapping. Air trapping. Because compliance increases, so you can inhale, but you can't exhale as efficiently, so the air stays trapped in the alveoli. Okay, I will see you guys tomorrow. We'll go through some questions, and hopefully I can clarify any confusing topics.